Great. It's wonderful to be here. It's a lot of fun to give tutorials, but actually what I've prepared is a two-part talk where the first hour is going to be mostly tutorial on Bayesian machine learning, and the second part of the talk will have maybe a short break in between. The second part will be some recent work that we've been doing on building an automatic statistician that is, as you'll see, going to be heavily based on the material that I'm going to talk about in the first part. So even if you sort of know the basics of Bayesian machine learning, feel free to open up your laptop, read your email, work on your ICML submission or whatever it is that you're doing, then you might want to pay attention again during the second part to hear about our recent work. Okay, so the work that we do in our group is very much focused on machine learning, a very broad range of topics in machine learning from the point of view of probabilistic modeling and Bayesian inference. So what I'm going to do is just start at a very high level and then work our way through some of the basics of Bayesian or probabilistic machine learning. Then we'll have some discussion of philosophical issues that relate to this, some algorithmic issues that relate to this. Then we'll have the break, and then we'll talk about the sort of putting it all together into the new research I'm going to describe. So what is machine learning? Well, the term is relatively new, but the idea is certainly not new. It's been around with different names for many decades. So there are many related terms such as pattern recognition, neural networks, which were in vogue in the 1980s and have been rebranded in the 2010s, data mining, and other fields like adaptive control and system identification, statistical modeling, data science. All these things are related. And, I'm going to use the term machine learning, but a lot of what we do could be rebranded in different ways if you come from slightly different communities. Okay, so this doesn't tell you what it is, just that it's related to lots of other things. It's also interesting to think kind of outside of the narrow view of machine learning and think about learning in general. So the topic of learning is something that has been studied by people in many, many different fields. Engineering, computer scientists, have thought about how to get computers to learn. In engineering, adaptive controllers are learning in some sense. System identification is about learning about a system. In statistics, a lot of parameter estimation can be thought of as just learning a model from data. Obviously, cognitive scientists and psychologists have been interested in understanding how humans and animals learn and what it means to learn and how it relates to things like perception, movement control, language, etc. People interested in neuroscience want to understand how the brain implements that sort of learning. So there's been a lot of work in that field as well. And even areas like economics, if you think about questions like, rational decision making or repeated games in game theory, or some questions in operationals research, or more recently, if you look at e-commerce, a lot of that has to do with learning about people and their decisions. Okay, so learning has been studied by lots of people in lots of different fields, but at least the good news is that although a lot of different kinds of people have thought about learning, there seem to be some common mathematical principles that keep emerging, revisited in different fields with maybe different notation, but the mathematics of systems that learn is, to some extent generally, agreed upon in some sense. So that's where the field of machine learning, I think, comes in. So what I'm going to just say is kind of a definition I've been using. Machine learning is an interdisciplinary field for all the reasons I've said, focusing on both the mathematical foundations and the practical applications of systems that learn, reason, and act. Okay? That's vague enough that I think it can capture lots of interesting things. But I'm going to make it more precise in a few minutes. Okay, so now within the field of machine learning, there have been a lot of different approaches, but I could broadly categorize them into two different ways of thinking about machine learning. One of them, maybe perhaps the predominant view of machine learning, is that it's a toolbox of methods for processing data. So, you've got some data, you feed your data into some algorithm, there might be many possible algorithms, and then you choose your algorithm or method based on perhaps some theoretical properties of that method, and hopefully also its empirical performance on some task that you call a learning task. Okay? Now, the way I'd like to think about machine learning is kind of more from the point of view of the science of learning models from data. Okay? So it's not just a black box that you feed your data into and you get some outputs. I want to try to think a little bit, I want us all to try to think a little bit about how we can put this on some foundations. So the way we're going to talk about that is we're going to define a space of possible models for data, then we're going to learn the parameters and structure of the models from the data, and then we're going to use that to make predictions and decisions. So in practice, it's not going to be all that different, but the sort of foundational stuff that we appeal to here is different than here. Okay? All right, so let's focus on this view. And kind of more specifically, the view that I'm going to try to describe is based on the concept of probabilistic modeling. So, first of all, what's a model? A model is, in a sense, a description of possible data you could observe from some system. Okay? If a model, I'm talking about model in a very general sense that might be used by somebody in the sciences, for example, as well. If a model can't make any predictions about observable data, then it's hard to falsify that model. It's hard to know whether that's a good model or a bad model. So the lens with which we're going to evaluate models is in terms of possible data they could predict. Okay, now of course, if you're going to use models to predict possible data and you're going to learn about the models from previous observed data, then, well, when it comes to predicting possible data, then we're never going to be certain about our predictions. If we could be certain about our predictions, if the model was certain about our predictions, then, in a sense, the task is solved, then you don't have to do anything. You know what's going to happen, and so you're done, right? Maybe the system is very simple, and you can predict exactly what's going to happen. But fundamentally, in all modeling, in all realistic scenarios, there is uncertainty. There's uncertainty in terms of the measurement noise of whatever you're measuring. There's uncertainty perhaps in terms of the parameters of that model. And there's uncertainty even about whether that was a good model or a bad model or even the choice of models. So the basic principle that we're going to use is to use the mathematics of probability theory to represent all forms of uncertainty that we have in modeling. Okay? Now, the good news is, if we use probability theory to represent our uncertainty, then we can simply continue to use probability theory to do all sorts of things like infer unknown quantities from observable quantities, to adapt our models, to make predictions, and in general to learn from data. So we don't need to appeal to arbitrary choices when the question comes, how do we learn this model from data? Well, we've expressed all our uncertainty with probability theory, and we can simply use probability theory to learn from data. Now, this view tends to be called the Bayesian view, but the term Bayesian was actually invented by a frequentist early in the 20th century as a sort of slur against people who use probability theory. And I think it would be easier if we didn't call it Bayesian at all, if we just said we're following the rules of probability theory, just like, we don't call everybody who uses calculus a Newtonian or a Leibnizian person, right? So calculus is the mathematics of rates of change. Probability is the mathematics of uncertainty. And I don't really see it as controversial to use probability theory. Okay, of course, there are plenty of people out there who disagree with me. All right? Okay, so we're going to just use probability theory. It sounds a bit boring, and it's actually very simple. So let's talk about it. It turns out this is not a picture of Thomas Bayes. It's a long story, but we always use that picture. Well, it's not even a depiction or drawing of Thomas Bayes. Okay, so Bayes, Reverend Thomas Bayes, who's buried, not far, somewhere in London, basically outlined a very simple rule for updating probabilities. And here's the way I'm going to write it textually, and then we're going to write it mathematically in the next couple of slides. So textually, what this rule says is you have some set of hypotheses, okay, or models. Before you observe the data, you're uncertain about those hypotheses or models, and you're going to represent your uncertainty by using probability. So you put down a probability distribution over all those possible hypotheses. Then you observe the data, and now because each model or hypothesis was meant to be a probabilistic description of possible data, then for every model or hypothesis, it actually assigns a probability to the data that you observed. This term here is called the likelihood. Then by the basic rules of probability theory, as outlined by Thomas Bayes, you multiply the prior times the likelihood. You renormalize it with a constant here that doesn't depend on your hypotheses. And what you get is a posterior distribution over your hypotheses given your data. And that's learning from data. This is what you knew before observing the data. This is what your data tells you about all the possibilities that you were considering. And this is what you know after observing the data. Okay? So Bayes' rule tells us how to do inference about hypotheses from data. Learning and prediction can be seen as forms of inference. All right, so to make that a bit more concrete, I'm going to just very rapidly go through some canonical, very simple problems in statistical estimation or machine learning, and then show you how this maps onto what I described. So these are going to be linear classification, polynomial regression, and clustering with Gaussian mixture models, or you can also think about it as density estimation. So very quickly, what is linear classification? Okay, well, the ingredients we have in every machine learning problem are as follows. We better have some data, otherwise it's not really a machine learning problem. So here the data are going to be pairs of x's and y's, where you have n data points. This is the data set. You have n data points. Each one is a pair. X is some features that you measure about some object. Maybe that lives in a d-dimensional real space. And y is some class label. So let's say you're classifying cats versus dogs, and these are features that you extract from images. Okay? And so linear classification corresponds to finding a plane that separates your cats from your dogs. So how do we formalize that in terms of a model? Well, a very simple model here would be that the probability of the label, say cat, given some parameters in the model, which I'll get to in a second, and an input location or features x, is for a hard classifier, it could be, for example, 1 if you lie on one side of the linear boundary and 0 otherwise. Okay, that's a very simplistic model, but it is nonetheless a model of data. It doesn't handle uncertainty very well, because it's got ones and zeros here, but it's a model of the data. Now, what ingredient does this model have? Well, this model has parameters. Okay? So in this case, the d plus 1 parameters that define a hyperplane in d dimensions. All right? And what is learning? Well, our goal here is in general to infer the parameters from data so as to predict future labels of future points. And that's called generalization. If you get a new image, you want to be able to tell whether it's a cat or a dog, and what the probability is that it's a cat or a dog. All right? So very quickly, now let's switch to polynomial regression. Now our data are pairs of x's and y's, but these are both reals. So these are these red dots where y is on this axis and x is on this axis. Our model is going to be, for example, an mth order polynomial with some noise added, where let's say our noise is Gaussian. I'm just making arbitrary choices here. You can make different choices if you want. I'm just showing you as an illustration what a possible model could be. Now, what are the parameters of this mth order polynomial? Well, they are the coefficients of the polynomial, like, the coefficients that define this blue line, let's say, the m plus 1 coefficients, and maybe the noise variance or noise standard deviation is also a parameter of your model. So these are our parameters, and our goal is going to be to infer these parameters from the data so as to predict future outputs, future y's given x's. Okay? Any questions so far? Okay, the third canonical example I'm going to mention is clustering with the Gaussian mixture model or density estimation. So this is what's called traditionally an unsupervised learning problem. Our data are simply points in some d-dimensional space. Here they would be the blue dots in two-dimensional space. Our model is going to say, I think the points come from a mixture of m Gaussian densities, in this case bivariate Gaussian densities. These pi's represent the proportion of data captured by each of these m densities, and pi of x is simply the ith Gaussian density parameterized by a mean and a covariance matrix. So the center and the shape of that ellipse, essentially. So the parameters are the means and covariance matrices of all our Gaussians and this mixing vector pi. And again, the goal is to infer these parameters from the data so as to, for example, predict the density of a new point, and perhaps maybe also infer which points belong to the same cluster. Okay, say like if these are genes, do these genes belong to the same sort of functional group in some way or whatever. Okay? So these different kinds of problems have the same ingredients, and almost every machine learning problem you'll see will have some of these ingredients in it, right? Most of these ingredients in it. Model, data, model has parameters, you're trying to make some predictions. Okay? So now, the basic idea, this is the sort of taking Bayes' rule. In fact, even going before Bayes' rule, we're going to use two basic rules of probability theory from which Bayes' rule is a corollary. The basic idea behind Bayesian modeling is that everything we're going to do follows from two simple rules. So the two simple rules are the sum rule and the product rule. The sum rule says that the probability of some variable x is the sum over y of the joint probability of x and y. Of course, if y is continuous, I'm going to replace the sum by an integral, but I'm not going to worry about that difference. Okay? The product rule says the joint probability of x and y can be factored either as the probability of x times the probability of y given x, that's what the vertical bar means, or the other way around, the probability of y times the probability of x given y. Okay? These are the two basic rules of probability theory. If you rearrange these rules in a particular way, you get Bayes' rule. And here I've simply written Bayes' rule in terms of the ingredients we saw in the previous three slides. In terms of a model, like for example the number of Gaussians that you have, the parameters of the model, like for example those means and covariance matrices and all that other stuff, and the observed data D. And now learning becomes the process of transforming what you knew before observing the data, that's the prior, that represents the sort of space of hypotheses that you're willing to consider in your model before observing the data. Then for all of these well-defined models, there is a likelihood function, which is the probability of the observed data given those parameters. Multiplying those two together, we get the posterior, which is everything we've learned about the parameters given the data and our modeling assumptions. Okay? I know maybe this is fairly basic for some people, but hopefully a useful refresher for other people. All right. So now what about prediction? So I said one of the things we have to do is prediction. Well, when in doubt, don't deviate from these rules. Okay? So what does prediction tell us we should do? Well, prediction, what is prediction? Prediction involves trying to predict some quantity X, maybe a future data point, or a label, or whatever it is, something we don't know yet, given the data and our modeling assumptions, M. Okay? And the sum rule and the product rule tell us that to predict this, what we have to do is we have to sum or integrate over all possible parameters, theta, the predictions for every one of those possible parameters, theta, that's what this term is here, times the posterior probability over those parameters that we computed from Bayes' rule here. So prediction, according to the sum rule and product rule, is naturally a process of averaging predictions over different parameter values, weighted by how much you believe in those parameter values given the data. Now note that whereas in most machine learning, the first thing that you start doing is optimizing parameters somehow, there is no optimization rule in probability theory. Okay? So there's a sum rule and the product rule. You can't make up another rule, say, I'm going to now optimize the parameters. That comes out of nowhere. And of course, a lot of machine learning and statistics is fixing the fact that you did something that came out of nowhere by adding regularizers and all sorts of other things. Okay, this is again, a caricature, and I do it myself sometimes if I need to, and it works really well if you have to, but it doesn't follow from the rules of probability theory. Okay? So that's prediction. What about model comparison? Well, we can apply the same thinking to compare different models M and M prime, let's say. Like, for example, if we're comparing fitting 3 Gaussians to 4 Gaussians to your data, M equals 3, M equals 4, which is better? Well, let's appeal to Bayes' rule here. We can compute the posterior over model classes given the data. And the term that comes in very important here is this term in red called the marginal likelihood. So by Bayes' rule, this is just the probability of the data given the model. That's the marginal likelihood. And by the sum and product rule, the marginal likelihood is the integral of the likelihood integrated with respect to the prior. Okay? Now, we're going to talk a lot more about the marginal likelihood, and the marginal likelihood, it turns out, is going to be really important for our automatic statistician in the second half. Okay? So, just to make things, make sure we're all on the same page, consider the very simple problem of you've got some data, you want to fit a Gaussian. Okay? Now, normally you would just fit a Gaussian by computing the mean and standard deviations of your data. But that's not actually that doesn't come from probability theory. So the way you would do it in a Bayesian setting would be, well, before observing the data, you need to specify a prior over reasonable parameters that Gaussian could have. All right? So, a prior over the mean and a prior over the covariance matrix of the Gaussian. You might need to know something about what kind of data you might be looking at. Is your data measured in nanoseconds or years, for example? That's relevant to what you choose for your prior on the mean. Okay? So you have a prior over the parameters, then you compute the likelihood for each setting of those parameters, and your posterior over the parameters will tend to concentrate on Gaussians that are reasonable given your data. But if you have very few data points, you'll be very uncertain about what the real mean and variance of your Gaussian is. If you have a lot of data, you'll be quite certain about what that is. Okay? Any questions about that? I'm waiting for somebody to ask, well, how do you choose the prior? Okay. Would somebody want to ask that?
How do you choose the prior?
I'll get to that. It's the reaction a lot of people have at this point, and basically I'll talk a lot more about that. But it's important, obviously. But that's it. This is really all there is to Bayesian machine learning. I mean, well, it's not all it, because then, I wouldn't have a job. I wouldn't be taking on PhD students who want to do machine learning research if that's all there was. Okay? Well, that's it conceptually, but there is the devil's in all the details. Okay, so now we'll talk about that a little bit. We'll talk about the conceptual side first, and then we'll talk about the details as well. All right, so here are the questions that I'm going to try to address. So first of all, I said we're going to appeal to the sum rule and the product rule. That's one motivation. But there are other ways of motivating why we might want to do Bayesian inference. So the sort of almost philosophical motivation. Then I'll talk about where does the prior come from. You ask the question, so you'll get the answer. And then we'll talk about the computational issues, which is how do we do these integrals? Okay? All over this stuff, there were some integrals, and it looks kind of harmless, but it's hard work. Mark is laughing. He knows it's hard work. It's not always harmless, right? Okay, so these are the things we're going to talk about. So let's just dive into it. So how to motivate the Bayesian framework. All right, so here's one motivation, which at the outset seems to have nothing to do with probability or statistics. So let's say we're trying to build an artificially intelligent robot. That's the kind of thing I thought I was going to be doing when I was 14 years old. Now I'm basically doing statistics, but they're sort of related, okay? So let's say we wanted to build some kind of artificial intelligence system. Now, in order for this system to behave intelligently, one way of doing that is for the robot to be able to represent its beliefs about propositions in the world. Like, where its charging station is, and whether there's a wall here or a door, or whether this thing is hostile and it's going to shoot it, or whatever it is that the robot needs to do. Okay? So it's going to be representing beliefs about the world. Now, in the robot's brain, we need to be able to represent these beliefs somehow numerically. Okay? So the question we're going to ask is, if we want to represent the strength of these beliefs numerically, what are the mathematical rules we should use to manipulate those beliefs? Okay, somewhat abstract question. Now, it's a question that it turns out has been thought about since the 1940s. So what I'm going to describe is kind of the view that comes from the Cox and Jaynes axioms. It's Edwin Jaynes' book in 1996 describes this in great detail, very nicely, and Kevin Van Horn has a more modern description of the same stuff in 2003. Okay, so here is the basic idea. We're going to use this notation B of x to represent the strength of belief in, or the plausibility of some proposition x. Okay? Now, we're going to say, okay, B of x is going to be between 0 and 1. B of x equals 0, we're going to define as belief that something is definitely, x is definitely not true. And B of x equals 1, x is definitely true. So the extremes of this correspond to logic. What about in between? Well, in between, we're also going to be talking about quantities like B of x given y, which is the strength of belief in x, that x is true, given that we know that y is true. All right? Now, I won't go into it in great detail. It's about a chapter in Jaynes' book. But the basic idea behind these Cox axioms is that we want this belief function to satisfy certain intuitive properties. In particular, we want to represent these strengths of beliefs by real numbers somehow. So there's gradations between 0 and 1. We want some qualitative correspondence with common sense, and I won't go into that right now. But importantly, what we want is consistency. So if a conclusion can be reasoned in several ways, we want that each way should lead to the same answer. So that's sort of an axiom that we need for our mathematical rules. We also want that this agent or robot must always take into account all relevant evidence. So we don't want to be able to arbitrarily ignore certain things, to be kind of a rational belief manipulating system. And we also want equivalent states of knowledge to be represented by equivalent plausibility assignments or belief vectors, in a sense. Okay? It turns out if you agree with these Cox axioms, then a consequence of that is that belief functions must satisfy the rules of probability theory. The sum rule, the product rule, and of course Bayes' rule, which is a corollary of the sum rule and the product rule. So we can use probability theory to describe not just things like coin tosses, how many times is this coin going to come out heads, which is the classical use in frequentist statistics for repeated experiments, but we can use probability theory to talk about questions that are all about belief of events that only happen once. So we can say, what is the probability that a Democrat will win the next US presidential election? That's not a frequency in any sense of frequentist statistics, because an election only happens once, and that is a subjective belief, and different people can have different beliefs, and so on. But it's perfectly fine for the use of probability theory in that sense, according to the Cox axioms. Okay? Now, on top of that, if we're gambling people or gambling robots, then we should pay special attention to our use of probability theory here, because if we are willing to accept bets with odds proportional to the strength of our beliefs, so for example, if we believe some proposition with strength of belief 0.9, and that implies that we'll accept a bet that gives us odds that are greater than 1 to 9, right? Then unless your beliefs satisfy the rules of probability theory, including Bayes' rule, there exists a set of simultaneous bets which you would accept and which you're guaranteed to lose money no matter what the outcome. All right? That's pretty bad news. It's not that you're expected to lose money. It's that you accept all these bets and, you're stuffed. Okay? You'll end up with less money than you had before. So your beliefs, it doesn't matter whether they're right or wrong, but they better be coherent. They better, your belief in X and your belief in not X better sum to 1, for example. Okay? The only way to guard from that is for your beliefs to satisfy the rules of probability. Okay, now what happens, people are very worried about, you're injecting a lot of subjective knowledge, by having these beliefs, so what happens when you actually observe some data? So some more classical statistical results relate to what happens when you observe lots of data. So asymptotic certainty tells us that assume you have a data set D sub n consisting of n data points, and imagine it was generated from some true parameter theta star of some probabilistic model. Okay? Now, under some regularity conditions, which I won't go into, but they're important, as long as we assign prior around theta star, which is non-negative, okay? So what we ideally want to do is give non-zero probability density at theta star and also non-zero probability mass around theta star. And what does that mean? That means as long as under our prior theta star was not impossible, then the nice result is that under our posterior, in the limit as n goes to infinity, our posterior is going to put more and more mass around theta star. So it's going to converge to a delta function on theta star. So a lesson here is, don't say something is impossible, because if your data starts supporting that, then you never can recover from that. So you better put some probability mass on all sorts of crazy things. Like you are all aliens and I'm having a dream or whatever, that there has to be some possibility of that. Otherwise, the data would, I would never be able to overcome the data. Okay? All right. So now what happens in the unrealizable case, where the unrealizable case is just when data was generated by some probability distribution P star of x, which cannot be modeled by any theta. Okay? So it's outside the space of models that you've considered. Then the good news is the posterior will converge to theta, a delta function on theta hat, where theta hat is the distribution in the space that you're considering with lowest what's called KL divergence to P star, the true distribution. And the KL divergence is just a measure of how different these two distributions are. So it converges to the nearest thing you can find, and that actually ends up being the maximum likelihood distribution. The maximum likelihood parameters. So even in the unrealizable case, the worst you can do is to be like maximum likelihood in the limit. Okay? All right. That's asymptotic certainty. Asymptotic consensus tells us what happens if you have multiple Bayesians with different beliefs. Okay? So, and this is always, this is often going to be the case. Different people could come into a modeling scenario with different priors on what's actually going on. Okay, so consider two Bayesians with different priors, P1 and P2, who observe the same data D. So what's going to happen here? Okay, well, assume both Bayesians agree on the set of possible and impossible values of theta. In other words, assume that the thetas that P1 gives non-zero probability to are the same thetas that P2 gives non-zero probability to. All right? This is important. That means that the two Bayesians have different priors, but they're not being completely dogmatic and saying what you're saying is absolutely impossible to each other. Okay? Because if they do that, then, good things don't happen. But if they agree on the set of possible and impossible values of theta, then in the limit, the posteriors will converge to each other. Okay? So they observe more data and they converge to the same beliefs eventually. All right? That's what you'd like from a learning system. You'd like that if the data is overwhelmingly telling you something, you will converge to something that is consistent with what other learning systems would also converge to. Any questions about that? I'm not going to do any demos because for two reasons. One of which is I'm running it on this desktop here, not on my laptop. The other one is because my MATLAB license isn't working anymore. So I discovered on the train. So no demos, but that's okay. All right. So that's asymptotic consensus, and that's kind of the summary, I think, of the philosophical motivations for doing Bayesian stuff. Of course, there's some practical issues, and there are lots of reasons why a lot of people don't like to do the Bayesian stuff, which I'll hint at later on as well. Okay. So, here is just a simple problem to think about. Here's a simple probabilistic calculation. Consider a binary variable relevant to today, rain or no rain for weather, okay? Or it could be heads or tails for a coin. Let's call it 1 or 0. And let's say you have a bunch of data. Now, and you're going to use a Bernoulli distribution, which has some parameter q between 0 and 1, which is going to be the probability of rain, let's say. And the Bernoulli distribution is q to the xn, 1 minus q to the 1 minus xn. So here's a couple questions. Is this a sensible model? Okay, somebody from this side of the room. If nobody answers, I'm going to get more specific. Okay, somebody from the back half of this side of the room. Then I might use my laser pointer. Do you think this is a sensible model for the weather in London? Yeah? Yeah, so if it's raining all the time, Q would be very close to 1 or something, right? Okay, but, what about, is the rain on, if this is successive days, n1 through n going from 1 to n, is that a reasonable model? No. Yeah, I mean, it's not a reasonable model in the sense that rain, there seems to be some autocorrelation in rain. If it rains one day, it's more likely to rain the next day. You can have a spell of sunny days. You wouldn't be able to tell, actually, but there is a little bit of autocorrelation even in a place like London. Okay, so it's not a sensible model, but that's fine. We can come up with more complicated models. This is just sort of for a simple probabilistic calculation. Okay, now imagine we want to learn the model parameter Q. We start with a prior and condition on the observed data. For example, we could start with a uniform prior on the interval between 0 and 1. Okay, that's a prior. Now, what is the posterior after observing one rainy day? What does that look like? Anybody? You could do the calculation if you want. It's not a number. Okay. So the type of your answer doesn't match the type of the question. The posterior is a distribution. Okay. So you're saying it's a delta function on Q equals 3/4? It's what I'm asking for. I'm sort of on purpose a bit vague because it helps draw out questions. Actually, what I'm asking for is what is the posterior distribution on Q after x1 equals 1? Is this a pen? Yeah. P of Q given x1 equals 1. All right. When in doubt, what should you do? Yep. Huh? When in doubt, use the sum and product rule. Yeah? Okay. Yeah? 2Q. Right? Why don't you tell everybody why you think it's 2Q?
Well, the reason I think is because we multiply the prior by the likelihood. Prior is 1. The likelihood then is Q. And we have to normalize it, and the integral over Q will be only a half. So that's why
Brilliant. Okay. So this is, according to the sum and product rule, this is the prior times the likelihood, normalized. Okay. This was 1 on the interval between 0 and 1. The likelihood was, because x1 equals 1, that's just Q. Q times 1 is Q. And so this is Q over 1/2, this is a normalizing constant, which is 2Q. And as a picture, what does this look like? It looks like a distribution. I don't know if you can see this pen. Is this pen okay? It's a distribution that looks like this between 0 and 1, and it has a value 2 at the top. And it integrates to 1. Okay? So that's interesting. What is the maximum likelihood value of Q? It's running away from me. Going up to the sky. What is the maximum likelihood value after x1 equals 1? Yeah. So, okay, I mean, these are all very trivial questions, and for most of you, you'll be saying, why am I wasting my time? I should get back to writing my emails or whatever. But the maximum likelihood, because the prior happened to be uniform, the maximum likelihood value also matches the maximum a posteriori value in this particular case. and it's Q equals 1, which is like an unfortunate, overseas student arriving in London. It rains the first day, and the maximum likelihood student infers it is going to rain with certainty every day I'm in London. Okay? If your robot or your new student did that, you wouldn't think that was very clever. On the basis of one observation, obviously maximum likelihood is a silly thing to do. But the Bayesian answer of what do you think is the probability, after observing one rainy day under this prior, what do you think is the probability that it'll rain on the second day? Anybody? But you have to do a bit of math in your head. What does it look like as a picture? So the question I'm asking in mathematical terms is this. What is the probability that x2 equals 1 given x1 equals 1? Rain on the second day, given that it rained on the first day, assuming this uniform prior that we had. Two-thirds. Yeah, it's 2/3, which is possibly the answer you gave before. Yeah, or you said 3/4, but yeah, close enough. Okay, 2/3. Okay, the pen is giving out on me, but 2/3 is the answer, and that is just because the average value of Q, it ends up by the sum and product rule. You end up having to integrate over all possible values of Q according to this distribution. And the mean of Q for that distribution happens to be 2/3. Okay? So you observe one rainy day, you think, 2/3 chance it'll rain tomorrow. Okay, and then you keep updating your probabilities over time. All right, okay, I know this was like, come down. Basic, it's a bit of basic math, but it's important to sort of just wrap your head around what's going on here, okay? We're just using the rules of probability theory. There's nothing magical. And the answers actually end up being sensible. There's no other answer you could have if you had that prior. If you have a different prior, you would have a different answer, of course. Okay, so we're gonna switch gears, and we're gonna start talking about kind of more advanced and more interesting questions, which again are gonna relate to this automatic statistician that I'm going to talk about in the second half. And the really interesting key question that I want us to look at is this question of model selection. So imagine we have these 8 data points, these red data points. These are y's, pairs of x's and y's, and we're trying to fit y as a function of x. And we could fit a constant, linear, quadratic, cubic. I'm constraining myself to polynomials just to keep it simple. Say all the way up to 7th order polynomial. Okay? Now, what do you think is a good model for the data? Anybody? Okay, how many people like this model? Raise your hand if you like this model. Why not? It's going through every data point. It's a fantastic model of my data. Okay, so it's predicting, 50 between these 2 points, and then it's zooming down off the charts, but it fits my data perfectly. But all of us have the intuition that that's not a good model of the data. On the other hand, how many people like this model? Actually, some of you might want to go for this model. Come on, somebody. Yeah. You've only got 8 data points. You don't know that there is even a relationship between x and y. So you're going to fit a constant. And this one fits some structure, but maybe it's overfitting. I don't know. But probably most of you would look at this and you would say, maybe that's reasonable, I don't know whether that's reasonable, maybe that's reasonable, maybe that one, I think these are too complicated, right? What we want is our intelligent machine learning algorithms to behave like that. So how do we do that? Okay, do we need to go outside of the sum rule and product rule to do that? We need to add do we need to add minimum description length and fuzzy logic and regularization to be able to do that? No, it turns out we don't, okay? So how does that happen? Okay, well, this was just the polynomials example is meant to be an example of a more general thing that props up everywhere in machine learning and also in statistics, which is the question of model structure. So if you're doing clustering, how many clusters do you have? If you're doing dimensionality reduction, what should be the underlying dimensionality? If you're trying to predict, here, this is the Japanese bond market. You're trying to predict the Japanese bond market from hundreds of variables. Which ones are the relevant ones? That's a model selection question. You're trying to fit a dynamical system to some robot or something, or doing state space modeling. What should be the dimensionality of that? Hidden Markov models, how many states should you have? Source separation, how many independent components should you have? Or maybe you're trying to fit a graphical model to data. Which graphical model should you choose? All of these are model structure learning problems. Okay? And so they're the same kind of problem as this problem, and all we're going to do is appeal to the sum rule and product rule. All right? So how does that work? Well, it turns out when we do model comparison, if we're comparing different structures of models, different M's in this notation, and we use Bayes' rule here, this quantity in red, this quantity called the marginal likelihood, which I've described before, is the integral of the likelihood with respect to the prior. That quantity does some kind of, I don't want to say magical or mystical because it just comes from the sum and product rule, but it automatically achieves this Occam's razor principle, which is a preference for simpler explanations rather than more complicated explanations. Okay, so the marginal likelihood, written as this equation here in terms of this integral, we can interpret that in three equivalent ways. This term is also sometimes called the model evidence. And the three equivalent ways of interpreting that might give you some intuition for how they are penalizing complicated models. So one interpretation is that it's the probability that randomly selected parameters from the prior would have generated data set D. Okay, so one way of approximating this integral is to pick random parameters from the prior and see what the likelihood is that they give to D. Not the best parameters, so it's not the best seventh order polynomial that we should care about. Sorry, I went too far. Because the best one goes through all data points exactly. What would happen if I picked a random set of coefficients according to some prior? Then they would be, on average, very lousy, right? Whereas these might be, on average, much more reasonable. Another way of saying the same thing is that it's the probability of the data under the model averaging over all possible parameter values. That's just a verbal description of that equation. Or if you like information theory, log of 1 over this marginal likelihood is a number of bits of surprise at observing data D under model M. Where surprise is a technical thing that they define in information theory, where entropy is the average surprise. Okay? But, in English, what that says is we should prefer models for which the data is not too surprising. Okay? That's what's going on here. Now, model classes that are too simple are going to be unlikely to generate that particular data set, and model classes that are too complex can generate many possible data sets, like that seventh order polynomial. So again, they're going to be unlikely to generate that particular data set. And the kind of the middle case is models that are just right in some sense. So a way of representing that pictorially is imagine that you have all data sets of a particular size along this axis here, and different model classes spread out their probability mass in different ways. So very complicated model classes will generally spread their probability over many possible data sets. Very simple models, like this green one, will concentrate their probability on certain simpler data sets. And when you observe any particular data set, you can reject models for being either too simple or too complex.
Right.
Yes?
So if you have data that's generated by a simple model, say it actually is Gaussian data, and you get more and more data, are you saying that you then should use a more and more complex model?
No. This is a picture for what happens for a particular data set size n. I'm fixing the data set size n. I haven't told you what happens to this picture as you increase the data set size. The story is more subtle, actually. I've kind of written, I've sort of half written a paper just about sort of this story, what happens to this as you get more and more data. But essentially what this says is if your data actually came from a single Gaussian, then that model of a single Gaussian will give it higher marginal likelihood than a model with 10 Gaussians. Because a 10 Gaussian one is spreading its probability mass over many possible data sets. The principle that's important here is the conservation of probability mass, in a sense. Okay, a model, whether it's simple or complex, it has to produce a probability distribution over these data sets. So a more complicated one can spread its mass, can gamble over many more alternatives, but it can't win everywhere. Okay, it has to sacrifice in some places. Okay, we're almost at an hour. Let me see. I want to just get to the algorithmic side very briefly, and then we'll pause and take a 5-minute break then. Okay? And of course, if you have to leave at 3, this is 3, so you can leave now. So you can leave now. Yeah. All right. Okay. So here is Bayesian Occam's razor at work. This is in the polynomials example. What I've shown you is those same 8 data points, the maximum likelihood fit in blue, and then in green is samples, 20 samples from the posterior for each of the models up to 7th order polynomial, showing you kind of the uncertainty that they have when they make predictions, etc. But the important thing is the plot here on the right, which shows you the marginal likelihood or model evidence as a function of the model order. So what this basically says is, for the priors that I chose, and I chose them sort of very simply out of the box, normal zero mean priors on the coefficients, and an inverse gamma prior on the noise variance, because then the integrals that come out all to be exactly computable. For those priors, the picture that you get is as follows. It says 0th order seems like a reasonable hypothesis. First and third order also somewhat reasonable hypotheses. Second order seems to be the most reasonable hypothesis given the amount of data you've seen. Higher orders have some probability associated with them, but it's rapidly decreasing, so you can't see it on this plot. Okay? If I chose different priors, I would get a different picture here. And that has to be the case. That makes sense, because different priors correspond to different assumptions about the ranges that these coefficients can take. A model which says the coefficients of a polynomial range between -1 and 1 is a totally different, it's a very different model than the model of the same order where you say the coefficients range between -1,000 and 1,000. So this picture will be sensitive to your choice of prior, but the basic properties of this picture that you can reject models either for being too simple or too complex, that property will generally remain. Okay. So this is Bayesian Occam's razor in action. All right. All we did was use probability theory. Okay. So a couple of last points, which is where does the prior come from? Okay, so there have been a lot of attempts at coming up with ways of choosing priors. There's a whole branch of statistics called objective Bayes, which tries to come up with objective ways of coming up with priors. And what that ends up being is choosing forms of non-informative priors that try to capture some form of ignorance and have good frequentist properties. It's very interesting, but it kind of misses the point, I think, of what the Bayesian modeling framework is about. Now, often you have hierarchical priors. These are not mutually exclusive things here. I'm just talking about different kind of aspects of how you choose priors, where you have some parameters and you have hyperparameters, and you don't know what the hyperparameters of your model should be. These are these alphas, so you put a prior on the hyperparameters, and then you say, well, I don't know what the hyperparameters of the hyperparameters should be, so maybe I should put a prior on that as well. It turns out you could keep going, but it doesn't make much sense to keep going up, because at some point, all of this just corresponds. You could collapse all of those levels higher up. It corresponds to some prior over theta. Okay, so don't sweat over it too much. You don't have to keep going infinitely up. You just go up until you've coupled together parameters reasonably, and then you can stop there. You might have different parameters you want to couple together in a hierarchy. Then there is this sort of empirical Bayes approach, which is you try to be Bayesian about theta, but then maybe at the level of alpha, which is the hyperparameters over theta, you basically say, instead of putting a hyperprior on those, I'm going to optimize those to the data. So you're kind of doing a mixture of maximum likelihood and Bayesian inference, sometimes called type 2 maximum likelihood. And this is usually a safe thing to do, but it's violating the sum and product rule, right? But it gives you some robustness in case you totally screw things up at the level of hyperpriors and so on. Okay? And now the last thing I'm going to talk about is subjective Bayes, so subjective priors, which basically says priors should capture our beliefs about reasonable hypotheses before observing the data as well as possible. And that's, when you say something is subjective, that doesn't mean it's arbitrary. It doesn't mean anything goes, because subjective should be, it captures our knowledge about the problem as best we can, and obviously somebody who knows more about something will have better priors than somebody who doesn't know anything about that problem. Okay? All right, so let me just focus in on the subjective view. So priors should capture our beliefs and knowledge about the range of reasonable hypotheses as well as possible. Okay, so you need to think a little bit about what reasonable hypotheses are. And why? Well, the reason is otherwise we, or whatever learning machine we're designing, will make inferences and decisions which are not coherent with its beliefs and its knowledge. Okay, so what's the point of following this whole philosophy if we're gonna, let's say we believe that this team is gonna win this football match, but then we place a bet that is completely incoherent with that. Okay, there's no point in doing that. Okay, if you believe something, if you're going to bet on it, if you're going to make decisions, then your decisions should be coherent with your beliefs. Okay, now then people worry. Well, how do we know our beliefs? Well, sometimes you have to think about the problem domain, and a good way of testing our beliefs is because probabilistic models will always be able to generate possible data sets. Before we observe the real data, we could generate from our prior. And we could look at that data, that fictitious data, and say, does that actually capture what we believe is reasonable in this problem domain? And that's a good way of testing our priors. Even very vague priors are useful because the data will eventually concentrate according to asymptotic consensus and asymptotic certainty. It'll concentrate around some reasonable posterior in most cases. And the other thing I want to say is the key ingredient of Bayesian methods is not the prior, it's the idea of averaging over different hypotheses. Okay? The prior is needed for things to be well defined. Otherwise, your model is just not well defined. Okay? Because you couldn't generate possible data from your model. If you don't tell me what the range of parameters is, you can't generate possible data from your model. All right. I'm going to suggest we take a 5-minute or so break now. I will talk about a couple of things at the end of this, and then I'll switch to the automatic statistician. Okay.
So we need to drink water or something?
Oh, water. Water
Yeah.
would be good, yeah.
Mark, are you in? Somebody's talking down to me.
Okay. I'm gonna finish a couple of comments from the first part of the presentation and then switch into the second part, which should be shorter anyway. So we talked about subjective priors. I'll skip over this exercise. This is just an exercise in trying to come up with subjective priors. I give a tutorial on how to choose stupid priors, with the idea being that you should avoid choosing stupid priors. And you know, of course, your inferences are only going to be as good as the assumptions that you make and the data that you have. If you choose silly assumptions and you have lots of data, maybe it doesn't matter. If you choose silly assumptions somehow and you have small amounts of data, then it does matter. So, here is how not to do things. All right, step one. Choose an improper or uninformative prior so that your marginal likelihoods are meaningless. It turns out that if your prior is, say, uniform on the real interval, then you can't really compute marginal likelihoods in any sensible way. So that makes the whole endeavor a little bit problematic from the beginning. But yet there are a lot of people who try to do that sort of thing. Alternatively, you could go the other way and you could say choose a very dogmatic prior that can't adapt to the data. All right, I'm going to put all my prior mass on linear models with coefficients between -1 and 1. Well, if your data looks blindingly obviously like a quadratic polynomial, your model will still try to find the best linear model. So don't be too dogmatic either. Be careful when you put zero probability mass on things. Think about, do you really want to put zero probability mass on those things? Another thing you could do is you could choose a prior that's very hard to compute with. Okay, now you might be capturing your beliefs really well, but let's be practical here. If you choose a prior that's really hard to compute with a finite amount of computational resources, you might not be able to get very far. So it's actually kind of rational and sensible to choose priors that are easy to compute with when it doesn't cause problems otherwise. So after choosing your prior, don't look at it, don't think about it, okay? And I've seen a lot of people do that. Don't sample from your model and see what the data under the prior looks like. Some priors, if they'd only just sampled from the model, they would have been able to tell that prior is just ridiculous, that the data just could never look like that. Okay, but they never did that, so then they go and apply the sum rule and product rule, thinking everything's going to be fine, but everything isn't going to be fine. And then never question the prior, don't describe your prior in your paper so that your work is not reproducible, stuff like that. Okay? All right. Just a recap, this is what the whole framework is about. So the last thing I want to mention here is the computations involved, these integrals. So computing these marginal likelihoods can be computationally intractable. And that's either because the integrals are very high dimensional, your parameter space could be hundreds or even thousands of dimensions. If you have hidden or latent variables in your model, then you have to not only integrate over your parameters, but you have to integrate over those hidden or latent variables x as well, so the dimensionality even explodes further. And even your likelihood term might be very complicated to compute. Sometimes it's even impossible to compute that analytically. So for all those reasons, doing these integrals is a challenging computational problem. So just like we have a huge literature in optimization theory that we can appeal to when you're trying to optimize something, we also have a huge literature on approximate integration that we can appeal to when we have to solve these Bayesian inference problems. So just an example of some of those methods, going all the way back to Laplace. There's the Laplace approximation, which makes a Gaussian approximation around the posterior. There's something called BIC, which gives us a very simple penalty term for models that approximates the marginal likelihood. using the number of parameters in the model. There are variational approximations that I've worked on for many years, things like expectation propagation, Markov chain Monte Carlo methods, which you'll hear about from Ian Murray in 2 weeks. Other methods like exact sampling, et cetera, et cetera. So, on this slide, you're meant to despair because it's very hard to do these integrals. On this slide, you're meant to have lots of hope because lots of clever people have come up with lots of good ways of approximating these integrals. So these are the computational tools that we use for doing Bayesian inference. Now, I will make these slides available if people want. There is a bunch more material in this first lecture, which I sort of didn't expect to get to anyway, but they're in the slides. That includes descriptions of all of these things, like the Laplace approximation, BIC, variational methods, and a little bit of overview of sampling methods, MCMC, but you really don't need to look at these if you come to Ian Murray's lectures in 2 weeks. And then there's some interesting kind of discussion points, the myths and misconceptions about Bayesian methods, and how do Bayesian methods relate to big data problems, and just to kind of wrap up, let me just talk about these pros and cons of Bayesian methods. So the limitations and criticisms are that people who do Bayesian modeling generally just embrace subjectivity. They say modeling is all about writing down some assumptions, and we're just going to use probability theory to express those assumptions. A lot of people are uncomfortable with that. A lot of people think that the role of statistics is to lend some objectivity to the conclusions they want to have at the end of their paper. Okay? And that's actually kind of, I think, inaccurate. Now, another problem is that it's hard to come up with a prior. And I definitely acknowledge that this is an art. It requires some skills, some intuitions about being able to think about models in general. It's not just the prior. It's hard to come up with a model in the first place, or a class of models. And the automatic statistician that I'm going to talk about is sort of a way of trying to get around some of these issues. There is a closed world assumption that you need to consider all possible hypotheses for the data before observing the data. Bayesian methods can be computationally demanding, and the use of approximations for computational reasons weakens some of those coherence arguments that I gave you. All of that stuff about Dutch books and the Cox-James axioms, that was if you could be a perfect Bayesian. Of course, if you are only an approximate Bayesian, then you do need to worry a little bit because you can't be perfectly coherent because it's computationally intractable to be perfectly coherent. The advantages are the things that I said, the coherence, the conceptual simplicity, it's just the sum and product rule, modularity, you can compose these probabilistic models, different parts of them together into one big coherent whole, and then in general, often these methods have very good predictive performance. And I won't give you that here, but just in the next set of slides, I'll talk about the predictive performance. Okay. So that's it for the first part. There is 2 review papers that I've written that kind of summarize this style of thinking. One of them is a chapter from 2004 called Unsupervised Learning, and another one is a recent paper called Bayesian Nonparametrics and the Probabilistic Approach to Modeling. So you can read about it more there. What I'm going to talk about now is the work that we've been doing on something we're calling the automatic statistician. And this is joint work with James Lloyd and David Duveneau, who are PhD students at Cambridge, and Roger Gross, who's just finished his PhD at MIT, and Josh Tenenbaum, a colleague at MIT. Okay, so the motivation behind this work is the following. So we're living in an era, as we all know, of abundant data. And now the problem is we've got all this data, but there aren't enough people out there with the right skills to be able to make sense of all this data. So, for scientific reasons, in the scientific world, in the commercial world, even in society, think about like medical data or government data. Scientific data could be from, high throughput, large scale experiments. The problem is there are not enough statisticians, data scientists, machine learning people to be able to understand all this data. But, many aspects of statistical inference, I think, can be automated. And so one of the goals of machine learning and artificial intelligence should generally be to develop better tools for understanding data that require minimal expert input. So we're trying to build an automatic statistician. And, by trying to do this, we hope that we can provide a useful set of tools for understanding certain kinds of data. We've already been uncovering challenging research problems in automated inference, in model construction and comparison, data visualization and interpretation. And in general, I think it's a way of advancing the field of machine learning beyond just kind of the always have an expert statistician or machine learning researcher in the loop. Okay? So the way I'm going to structure my talk is I'm going to describe the ingredients that need to go into my automatic statistician first, and then I'm going to describe the system at the end. The good news is I've covered a bunch of the ingredients already. So some of this will be review from before the break. And there'll be a couple of new things I'm going to talk about. So here are the ingredients. The first ingredient is we're going to take a probabilistic modeling approach, as I've described already. And that involves basically this application of the sum rule and the product rule. And the marginal likelihood is going to play a really important role in our automatic statistician. So the marginal likelihood is going to be driving the automatic statistician's ability to compare lots of different models, as I've described before. Now, the third ingredient is the idea of nonparametrics, which I haven't described before the break, but I'm going to describe right now. So in statistics, we can distinguish between parametric and nonparametric models. Parametric models assume that you have some finite set of parameters, theta, and then given those parameters, any future predictions, x, are going to be independent of the observed data. So it looks a bit like this. P of x given theta and d. Given theta, well, it's independent of d, so we can just write it as P of x given theta. What that means is that theta captures everything there is to know about the data. If you have a finite number of such parameters, then that induces a kind of information bottleneck between past data and future predictions. So the way to actually think about this is you can think about modeling in general as the process, it's an information channel from past data to future predictions. Where time is not really relevant in the sense that future means anything you don't know, past means anything you do know. Okay? So a parametric model, because it has a finite number of parameters, has a sort of information channel that is bounded by those number of parameters, and that makes them not very flexible. Non-parametric models, on the other hand, assume that the data distribution cannot be defined in terms of such a finite set of parameters. So in general, in non-parametric models, we actually write kind of the same equations, but theta is infinite dimensional. So we can think of theta as an unknown function in some sense. And that's why non-parametrics ends up using a lot of stochastic process theory, because stochastic processes is the study of random variables that are functions, essentially. Now, because theta is infinite dimensional, the amount of information that theta can capture about the data can grow with the size of the data set. And that makes these models, the non-parametric models, more flexible. Okay? So Bayesian nonparametrics has been used a lot in the machine learning literature these days for all sorts of different machine learning applications, things like function approximation, classification, clustering, time series modeling, feature discovery models, etc. And generally what you find is that a lot of the jargon in this field involves around stochastic processes like the Gaussian process, the Dirichlet process, the beta process, the Poisson process, etc. And the reason it's, we use process is because we're talking about random variables that are functions or infinite dimensional objects. Okay, so that's why that terminology is used a lot, and that's why a lot of the field of Bayesian nonparametric ends up looking at sort of probability theory and discovering interesting things in probability theory that can be used for machine learning, and then extending those and coming up with efficient inference algorithms for those models. So that's another ingredient, Bayesian nonparametrics, that I'm going to use. A particular example of a Bayesian nonparametric model that our automatic statistician, what I'm going to show you, is based on is a Gaussian process. And in 6 weeks, I guess, or something like that, Carl Rasmussen will give you a tutorial on Gaussian processes, I believe. But I'm going to give you a mini tutorial now because you need to know it to understand what I'm going to talk about later. And, of course, Mark Diesenroth is an expert on Gaussian processes as well. So after my mini tutorial, you can ask him for everything else there is to know about Gaussian processes. All right, so consider the problem of nonlinear regression. So instead of polynomials, what we're going to do is think a little bit more generally. So for nonlinear regression, we imagine that we have some data, x's, and we're trying to map to y's. So y is a function of x, and we have these magenta data points. So our data set is a set of pairs of x's and y's. Now what we want to learn is a function f, in blue here, with some uncertainty on the predictions, 2 standard deviations in red shown here. Okay? Now, instead of what I showed you before, which was this polynomials example, we're not going to put priors on coefficients of polynomials. We're going to put a prior directly on the space of functions. Okay? So that's the difference between a parametric approach, say put a prior on 5th order polynomials or something like that, and a non-parametric approach, put a prior on an infinite dimensional object, which is this function f. Okay? So that sounds scary and daunting. How are we going to put a prior on functions from x to y? And keep in mind the pictures are all 2D because I can show you 2D pictures. But in general, x could be any space. It could be a high-dimensional vector space. It could be a discrete space. It could be text documents, whatever you want. Y is going to be continuous. Okay. So we're going to put priors on functions from x to y. And the Gaussian process prior that we're going to choose defines a distribution over functions, call it P of f, which can be used for Bayesian regression. So the simple idea is you put a prior over functions, you observe the data, then the posterior over functions that you get, in some cases, is actually itself also going to be a Gaussian process. So how do we manage to do that? This is an infinite dimensional object. We can't even store infinite dimensional objects in a computer, right? So we need some properties of that infinite dimensional object to hold. And in particular, the property that is interesting for Gaussian processes comes when we look at the vector f, an n-dimensional vector, of the function value evaluated at n different data points, x1 through xn. So bold f is an n-dimensional vector of function values. If you have a distribution over functions, then bold f is a multivariate random variable, right? N-dimensional random variable. The definition of a Gaussian process is that P of f is a Gaussian process if for any finite subset x1 through xn of points in our input space x, the marginal distribution over that subset P of the vector bold F is a multivariate Gaussian. So basically, it's a Gaussian process if, however you slice it up, the finite dimensional version is a multivariate Gaussian. Okay? Or the other way to think about it is we can go from univariate Gaussian to multivariate Gaussian, so from scalars to vectors, and from multivariate Gaussian we can go to Gaussian process, which is functions. Okay? So if you're sort of familiar with machine learning methods, we can place Gaussian process regression on a cube that starts out with linear regression and does 3 different operations to it to get different models. So starting out from linear regression, we can turn regression methods into classification methods. So these magenta arrows correspond to the classification analog of linear regression, which, for example, would be logistic regression. The blue arrows correspond to taking classical or maximum likelihood methods and turning them into Bayesian methods. So this would be Bayesian linear regression. And the orange arrows correspond to doing something instead of linear in the original space, linear in some feature space using the kernel trick. So if you know about these things, then support vector machines are either kernelized linear classifiers, or kernelized linear classifiers, or a classification version of a kernelized linear regression method. Okay, it's 2 different ways of getting to the same place. Gaussian process is a Bayesian version of a kernelized linear regression method. And of course, you can come up with something called the Gaussian process classification, which lives at this corner of the cube. Okay? But this is an aside. You can forget about this if it didn't make any sense to you. All right. So we have Gaussian processes. As a reminder, the Gaussian process, this is just the definition of a Gaussian process, like a Gaussian distribution, is parameterized by a mean function and a covariance function or kernel. So in particular, if I'm looking at the joint distribution of the function f at 2 different input values x and x prime, that bivariate distribution is bivariate normal with mean mu, which is this 2x1 vector, which is the mean function evaluated at x and the mean function evaluated at x prime stacked together, and a covariance matrix, which is 2x2, which is the kernel evaluated at x and x prime in all 4 combinations. Okay? So now the kernel in a Gaussian process method, or the covariance function, basically captures how much f of x and f of x prime covary. So it actually ends up capturing properties like smoothness properties of your function. When x and x prime are very close to each other, you expect the value of f of x and f of x prime to be very similar. If x and x prime are very far from each other in some sense, you expect their values to be uncorrelated in general. Okay? And that's what's captured by the kernel or covariance function. So here's an example of a kernel or covariance function, and these parameters are interpretable and they can be learned from data. So these are signal variance, the variance of the bias, noise variance, length scales, roughness, etc. Again, the details don't matter so much, just that we can learn about properties of a function from the data. And everything else is defined using the basic rules of probability applied to multivariate Gaussians once we've defined the kernel. So it's very simple to compute with. Here's just some examples of samples from a Gaussian process with different kernels. You can see that it captures, functions with different properties like rapidly varying or slowly varying, but very smooth, or kind of rough functions or non-stationary functions. Okay. But if you observe data, then the posterior from these different Gaussian processes ends up being quite similar anyway. You know, the error bars might look different, but they all seem to predict reasonably from the observed data, which are these blue points. Okay, now the last ingredient I want to talk about for the automatic statistician is this idea of change point kernels, and this is going to be particularly useful when we think about time series. Okay, so what we're trying to capture here is that a Gaussian process might be a good model of a time series for up to some point, and then there's something like a change point, there's some change in behavior, and we'd like to model after that with a different Gaussian process. So the change point kernel is a way of capturing that. So assume f1 of x comes from a Gaussian process with kernel k1, f2 of x comes from a Gaussian process with kernel or covariance function k2. Then if you define f to be 1 minus sigma of x of f1 of x plus sigma of x f2 of x, where sigma is some sigmoid function that goes between 0 and 1, like this, then essentially what you're saying is that the distribution of f is itself a Gaussian process where it has a particular covariance function or kernel, k, obtained by composing k1 and k2 using your sigmas. So intuitively, in one dimension, what's going on here is that the function f behaves like f1 up until some point tau, then behaves like f2 after tau. I'll show you some examples of that in a minute. Now, a generalization of that is what's called a change window or change interval, where essentially what we're saying is that the function is defined as a change point from f1 to f2 followed by a change point back to f1. So the function behaves like f1 up until some point, then starts behaving like f2, and then goes back to behaving like f1. And that's the representation of a change point kernel, for a change window. It looks a bit messy, but it's just what I said. It smoothly switches between f2, smoothly switches f2 between time tau 1 and time tau 2. This is all for one-dimensional time series now. Okay, we can generalize these in higher dimensions, but it's more complicated. Now, why would we need to think about that? Here's some real data that's kind of interesting. Okay. This data is solar irradiance data, measuring sunspot activity from the 1600s up until the present. And by eye, when you look at this data, you say, whoa, what's going on here? Right? What happened to those sunspots here? Well, I don't know. I actually don't know what's going on with the sun, but it's a well-known sort of phenomenon. This is called the Maunder minimum, where sunspot activity in the late 1600s and early 1700s was very rare for a long period of time. Okay? There's another effect in here. It's not hard to see, but actually it turns out that sunspots have a periodicity of around 10.8 or 11 years. You cannot really see that easily, but we're going to show you how our method can discover that. Okay. All right. So that's a change window. Here, what we would say is there's a window of time when functions looked very different from outside of that window. All right. So we have all the ingredients. So let me just explain to you how this system works. The basic idea is the following. So we're going to talk about just learning the kernel of a Gaussian process. The usual approach to learning the kernel is you parameterize the kernel with a few hyperparameters like we have here, and we optimize or infer these from data. Okay? Now what we're going to do is kind of different. So our approach is going to be to define a grammar over kernels that can generate lots of different kinds of kernels using some simple operations. And we're going to search over this grammar to discover an appropriate representation of the data and also something that's interpretable. Let me be a bit more precise. So by taking a few simple base kernels or covariance functions and two composition rules, kernel addition and kernel multiplication, we can span a rich space of structured kernels. So for example, the linear kernel gives us a distribution on linear functions. The squared exponential kernel gives us a distribution on functions with some local variation. The periodic kernel gives us distributions on functions with repeating structure. By combining these, for example, a linear times a linear kernel gives us a distribution on, surprise, surprise, quadratics. So by combining these, we can get polynomials out. Squared exponential times periodic gives us functions that are locally periodic. So approximately periodic if you look at them, but the periodicity might go away eventually. Linear plus periodic will give us periodic with a trend, etc., and we can do these in multiple dimensions as well to get additive functions and smooth functions, functions that are periodic in some dimensions and trending in other dimensions, etc. So that's what we're going to do. In particular, different kernels express a variety of different covariance structures. So these are the sorts of kernels we're going to use. The white noise kernel expresses like just noisiness, and we're going to be able to use that to model heteroskedasticity, increasing and decreasing amounts of noise. The constant kernel is needed to be able to capture shifts from zero, linear, smooth, periodic, as I mentioned. And then, different well-known kinds of things, like linear regression and Fourier analysis and a bunch of previously proposed methods, can be seen as different elements spanned by our grammar over kernels. Okay? And CP stands for change point, which is you have a change point between one, say we have a change point between one squared exponential and another squared exponential. So, function changes at some point. Okay, so the algorithm basically starts with the base kernels for the Gaussian process, applies different operations, addition, multiplication, change point, and change window, explores kernels spanned by the grammar. Then for efficiency, we're going to optimize those kernel hyperparameters rather than integrate them out. So that would be the top type 2 maximum likelihood that I described. But we're integrating over the Gaussian process functions because we can do that easily. Now, each resulting model is scored using the marginal likelihood, but we penalize by this Bayesian information criterion in terms of the number of hyperparameters that we've optimized. Okay? So these are the ingredients that we're using. So how does it actually work? So here is an example of a very interesting and famous data set. This is called the Mauna Loa carbon dioxide Keeling curve. So this is one of those Exhibit A kind of data sets that's been used in climate science, where they measured carbon dioxide concentrations at this guy Keeling measured carbon dioxide concentrations on top of Mauna Loa, which is a volcano in Hawaii, over many, many years. And the data kind of looks like this. This is interpolation. That would be extrapolation. And when the grammar starts learning, it starts from nothing. It tries out different kernels. So here, rational quadratic is one of the kernels that it tries. It can do very good interpolation, but its extrapolation doesn't look too good. So it keeps expanding this tree. So it says, okay, rational quadratic just says the function is somehow smooth at different length scales. But actually, periodic plus rational quadratic ends up with a higher marginal likelihood. And look, interestingly, the extrapolations are looking better as well because now it's learned about periodicity. But let's keep going. There's more to the data. There seems to be a trend. So squared exponential times periodic plus rational quadratic, this is what the search procedure is finding. That actually captures the periodicity, the trend, and sort of smoothness properties of the function. And look at the extrapolation there. That's even more plausible as an extrapolation. And then it can continue. So, here is, the thing that I have found before plus a squared exponential. I'm not sure whether that has higher marginal likelihood. At some point, it'll reach a model that is too complicated that basically it says, okay, I don't really need all that much complexity by Bayesian-Occam's razor. I'm going to start somewhere and start at the beginning and stop somewhere, which gives me a good interpretation of the data. Okay? So now what can we do with this? So this is another time series data set. This happens to be airline passengers over time, where this is the data period, and the dashed lines are extrapolation before and after. And what is evident in this airline passenger data is things like Christmas and Easter and other times when people travel a lot. Okay? So there's an annual periodicity in here. And basically, the algorithm automatically decomposes this function into a sum of a very smooth monotonically increasing function, an approximately periodic function with a period of 1.0 years, with approximately linearly increasing amplitude, and something weird with a period of 4.3 years, which actually is in the, we keep kind of improving the grammar, and actually now it's not even finding that anymore. Okay, but this was the sort of original decomposition that it had of the data set. Now, why is that useful? Well, one of the useful things here is, given the data, this text was actually produced automatically. Okay? So in fact, we're looking at two things. One of the things we're looking at is how well do we perform at prediction, and it turns out that this structured search method that I described for the automatic statistician is actually doing extremely well at predictive performance measured by mean squared error or negative log likelihood compared to other methods, both baselines and some state-of-the-art methods. But here's another example of predictive performance averaged over 13 data set. This is the Gaussian process automatic statistician here. 1 is the best performance. This is a commercial equation learning method called Eureka, which got a lot of press but doesn't perform very well. And here are a bunch of sort of near state-of-the-art methods. Okay? But what I think is really exciting about this is the potential to automate the interpretability. So by distributing the terms, we can actually help us interpret the data. So now, instead of finding that weird 4.3 year period for the airline data, we find a much better interpretation of the data in terms of these 4 components, the last one being just residuals. And then from that, we generate text automatically. So this is the latest work that we've done, where what we're generating is, I'll show you. So maybe for the airline data, whichever one, either the solar irradiance data or the airline data. Let's look at the airline data. Okay, this was automatically generated from our algorithm. It's a report. Okay. It's in the style of a NIPS paper, but we're not going to submit it to NIPS. Let's see, fit width. Okay, this report was produced automatically, see blah, and whatever. Executive summary. The raw data and full model posterior with extrapolations is shown in figure 1. Raw data, extrapolations. The structured search algorithm has identified 4 additive components in the data. The first 2 additive components explain 99.3% of the variation in the data, as shown by the coefficient of determination in table 1. After the first 3 components, the cross-validated blah, blah, blah increases by no more than 0.1%. This suggests that subsequent terms are modeling very short-term trends, uncorrelated noise, or are artifacts of the model or search procedure. Short summaries of the additive components are as follows. A very smooth monotonically increasing function, okay? Approximately periodic function with a period of 1.0 years with approximately linearly increasing amplitude, a smooth function, uncorrelated noise with linearly increasing standard deviation. Then the automatic report says, model checking statistics are summarized in table 2 in section 4. These statistics have not revealed any inconsistencies between the model and observed data. So one of the things we're trying to automate is model checking, which is actually quite a tricky thing in Bayesian inference. Can we identify things in the data which obviously the model does not capture? And in this case, it seemed not to identify. And then the rest of the document goes through each of the components in detail and shows you the component and the residuals and describes it for you. Okay? So, I could click on any of the other ones. Some of them are more fun. Okay, solar. Let's see, the solar. Yeah. So yeah, if we're submitting these to Turnitin so that if anybody tries to use this, then yeah. Okay. So here's the SumSpot data. Of course, it doesn't know what the data is, so the text is a bit boring. After you read 3 of these reports, it's a bit boring unless you care about the particular data set. But here it's using change points. So for example, it finds the second component is a function that applies, a constant function that applies from 1643 until 1716. So that was the Maunder minimum. And then smooth, and then the periodic component of 10.7 years it discovers as well, and then a bunch of other stuff. And it does model checking, which is quite good fun, and so on. Okay. So, we can obviously run many data sets through this. And we're trying to get it to be extremely robust to all the sorts of time series data sets that we can throw at it. And it does end up predicting, even it's interpretable, but also it's not compromising too much in terms of predictive accuracy. It's actually doing better than other methods. Okay, so there are, of course, challenges here, trading off predictive performance and interpretability. We do know how to get a little bit better predictive performance, but then the models don't come out so interpretable. If we throw in really powerful kernels, we get somewhat better performance, but it's very hard to write the report sensibly. The computational complexity of searching over a huge space of models is large. And, it's not like you get the answer in a few seconds. We have to run it for a couple of hours or something to get you the report. Translating complex modeling constructs into English language is hard as well. And so that's, not traditional machine learning research, but that's something we've been working on very hard. Now we're extending this to do all sorts of other things. So nonlinear regression, which is multivariate, where X is high dimensional. Classification, completing and interpreting tables and databases. We're linking it up to the area of probabilistic programming, which is a way of defining very general languages over probabilistic models. And just to summarize, the Automatic Statistician project is aiming at automating certain kinds of exploratory and predictive modeling. And conceptually, we're just following this Bayesian framework, relying in particular on Bayesian nonparametric models for flexibility. And we want to produce stuff that is interpretable by a reasonably numerate non-statistician. So we think our report never says Gaussian process in it, for example. Okay, our report should be readable by a scientist at least, that's not a machine learning researcher. And and we've sort of achieved that for time series, but there's a lot more that we could do. Okay, so finally, I'd just like to wrap up by thanking James Lloyd, David Duveneau, and Roger Gross, who are the main people who've been driving this research, and also my colleague Josh Tenenbaum. And that's just the review paper I mentioned before, but these are the 2 key publications around the automatic statistician so far. So that's it. Okay, thanks. Yep.
Fine. Thank you for a very very cool. I want to ask a little bit about your interpretability point in the challenge. Now, you said with more powerful kernels, you've got greater
Yeah.
weight. But that wasn't as easy interpretable. And it seems to me that there is some sort of, there's a conflict here with machine learning. That if machine learning says it does have greater weight,
Yeah.
then the challenge is to interpret it.
Yes, it's true. I mean, what we found is that for the most part, actually, when we made more interpretable models, most of the way it ended up with better performance. But then at the end, we could add in some very fancy kernels that could just suck up a lot of the internal structure of the data and gave higher marginal likelihood, penalized by BIC, but maybe didn't actually do as well in terms of extrapolation, didn't come up with as good interpretability, but had, by our metrics, had better performance in sample, right? And also maybe on held out in sample data if you just did traditional cross-validation or something like that. So I actually think there is a real trade-off, right? You know, if you want to be able to describe in English, you know, what your model is doing, then you might have to sacrifice doing something that's really, really good. But it's not that bad, and it's a lot better than what the equation learning people do. So in terms of, for example, these kinds of data sets, you can throw these, and we have thrown them at this sort of commercial equation learning method, and it comes up with a one-line equation, like, you know, y equals sine of x plus x squared plus whatever for your function. And keep in mind, we're not just writing down a function, we're writing down properties of the function, which I think is the right level at which to interpret this data. So when you write out this expression in terms of sines and logs and polynomials and so on, you get a very succinct interpretation of your data, but it's not very intuitive. You couldn't write a whole report about it, right?
So I guess I have one follow-up. Are there these complex kernels you talk about? Do you advise against using them full stop, or should there be something else done to maybe in how you select fires?
Yeah, no, it's I think that in some cases we might perform better if we do integration over hyperparameters rather than optimization, and that could be one of the issues going on here. I'll give you a very concrete example. It's the airline here, the airline data. Our final interpretable solution ends up using distributivity to decompose this thing into these components. Okay, and that's the way we structure our report. The first component that captures most of the data, plus the second component, plus the third component, plus the fourth component. Now, when we did the first paper on this, we didn't kind of write out our model in terms of this distributivity directly, and we threw in a very complicated kernel, such as the rational quadratic kernel, and that's when we got this weird artifactual thing, which was an exactly periodic function with a period of 4.3 years, because it needed to explain the residuals from these guys with something else. Okay? So we got rid of that, and we actually are performing better in terms of extrapolation, but sometimes it doesn't show up in the metrics. Because airline data, you wouldn't think that there's any reason there would be a period of 4.3 years. It doesn't make any sense. It's true. I mean, in some of these data sets, I have no idea, by the way, why their sunspots have a 10.7 or 10.8 year periodicity. Somebody here probably knows. Yeah. Yep. No, how do we do our structure search? We basically do it in kind of the same way as I've shown here, which is essentially a depth-first search. So basically, we we expand out one level, then we pick the best, and then we expand out from there. We don't do much backtracking, but we could. But we score these methods all with the marginal likelihood, so it's actually quite easy to evaluate these things. It would be hard to do something like a genetic algorithm sensibly because there isn't a natural reason why crossover and things like that would work well. But there are other people who have tried to do genetic algorithms to do equation learning, for example. I'm not sure if Eureka does that. It might. Yeah, Mark?
So in the first talk you said that the marginal likelihood takes care of the model complexity to some degree. So in this work, you add the BIC on top as a penalty. So
what's going on there? Yeah. Okay. So the real integral we want to do is the integral over the unknown function and the unknown hyperparameters. Okay? That would be the real marginal likelihood. But as you know, the integral over the unknown hyperparameters is a pain to do. The integral over the unknown function is very easy to do. So what we do is we compute the marginal likelihood integrating over the unknown function, but for the unknown hyperparameters, we optimize them. And because there are different elements of our grammar will have different numbers of hyperparameters, we need to use BIC to penalize that. So that's exactly why we're kind of combining these two terms. But it comes from approximating a single marginal likelihood. Yep.
Now there is a function in machine learning of making models deep.
Yes.
Without actually knowing why we make deep. So stack layers one over another. If you try to put hyperparameters on hyperparameters on this, and make layered models, this gives you anything regarding the results, because you mainly deep learning is all about results.
Yeah, okay. So I have a lot of things to say, and we don't have enough time to talk about this for deep learning. But let me make a couple of comments here. So one of them is we don't need to go very deep here to get good interpretability and good predictive performance because we integrate over the functions, so we just need a level of the grammar and the hyperparameters over the grammar. There's no real reason to go higher up than that because we could integrate those things out anyway. Now, the other thing to say about deep learning in this context is, to me, actually, most of the excitement about deep learning has been learning low-level perceptual features from data, like images, sounds, whatever. Okay? But I challenge you, anybody watching this video, to get me a deep learning method that produces a 12-page interpretable report about your data. Okay? So there is much more to machine learning than deep learning, despite what the media says. And part of the excitement for me is, yeah, okay, we seem to, if we're Google or Facebook or Microsoft, we seem to have basically solved the problem of extracting low-level features from vast amounts of data with vast numbers of computers. And we can use any of a number of old 1980s style pattern recognition methods for that. But the excitement is, where do we go from there? Okay, and I'm more excited about this, which is, let's get something that is really useful for people to be able to understand their data, that can talk to them almost like a human being would, or a statistician. Okay. Can I go to the person the far? Yeah. Okay. So demanding. Okay. So these are relatively short time series, and we run this structured search method on a cluster for a few hours. Okay. To produce a report. But if you care about your data, maybe it's worth waiting that long. Now, in the appendix slides, just in case somebody asks something like that, I have a whole bunch of stuff on how you scale up Gaussian. Now, we're using exact Gaussian process marginal likelihoods. which are cubic in the number of data points. But, for about, 10 or 8 years or so, people have come up with better and better ways of doing linear time Gaussian processes. So it's basically putting 2 and 2 together to get a linear instead of cubic time scaling with number of data points. But the search is still challenging. The grammar spans a very big space, but I think it's necessary. It's hard to get around that. Fortunately, you can parallelize this in a very easy way. You tell me when I have to. Can I take a last question from? Yeah. I should ask James, who's been doing these experiments. So it's like a few hours on a few dozen nodes, or a dozen nodes, or something like that. It's not, we're not throwing Google scale resources at this stuff. Okay. All right. Maybe I'll wrap up there. All right.